Hello everyone, I hope all of you are doing great. So today our group will be presenting our proposal for the windshield installation project. So in this video we will be discussing a number of points. That is, first we'll go over the pain point identification, then we'll go over value addition to business, that what value our product adds to IMC, then we'll go over what are the current existing design alternatives, and then how are we choosing among those designs, and that would be the selection of design through screening matrix. Then we'll go over the component selections, and then there would be budget, timeline, and what impact our product would be adding on IMC as a business. The pain point with the current manual labor intensive task is the ergonomic issues with workers experiencing back pain due to lifting of the heavy windshields. Furthermore, manual handling of the windshield poses chances of damage to the windshield. Additionally, the manual application of the sealant leads to material wastage as well as time wastage. Now we identify the value our solution adds to the IMC as a business. Enhancing the safety and comfort of the workplace can improve worker satisfaction and morale, increase productivity, lower employee turnover, and better retention of skilled staff are the results of this. Streamlining the windshield installation process and reducing ergonomic strain on workers can improve overall efficiency. This leads to faster production times and lower costs with reduced material wastage of the sealant. Furthermore, increased expenses may arise from the ergonomic problems as a result of worker injuries, lost productivity, and possible legal liability. Our solution would lower these expenses and boost the bottom line by taking proactive measures to address these problems. Moreover, material wastage is decreased by automated sealing application systems, which lowers the operating costs. Additionally, the automated system reduces chances of human error, increasing the quality of the windshield installation. This leads to less work for the quality control department as well as lesser warranty claims. Furthermore, exhibiting a dedication to ensuring the safety and well-being of employees can offer a competitive edge. It can improve your company's standing as a responsible and progressive one, drawing in clients that respect morality and environmentally friendly business methods. We now talk about our system, and our system on a broader level can be broken down into two subsystems. One is the sealant application system and the other is the transport system. To define the sealant application system, it is the system that is going to apply the sealant on the windshield, and then the transport system would lift it from the sealant application station and transport it all the way towards the car, where the worker then slide it down and install it on the car. We'll explain the system in detail in this presentation. We first go into the details of the sealant application system. Currently, industry around the globe utilizes 6 degrees of freedom industrial manipulators for the purpose of applying the sealant to the windshield. Industrial manipulators offer a number of advantages because of which they are used. Firstly, they are very time efficient and can accurately trace out the sealant trajectory, minimizing material wastage. Furthermore, they are very suitable for higher throughputs. However, these robots require their own space and cannot operate in industries where space is constrained. Moreover, they are very power hungry and are also very expensive, leading to higher capex. On the other hand, another solution that could be used for the sealant application is an XYZ Cartesian gantry, much like the 3D printers that we see. The advantages of this is that it's a low-cost solution. It's also highly accurate for sealant trajectory control. It's suitable for the higher throughputs. It's suitable for constrained space where you need to have a low spatial footprint. Furthermore, it also has a very high repeatability for programmed paths like we have for our windshield trajectory. But it's a power-hungry system, and it does have a moderately high OPEX. We now do a detailed comparative analysis of the two methods. So both of them, as we see, that can be used for highly accurate sealant trajectory control. So now how do we compare them? We compare them based on the need that we have. We need to apply the sealant to a windshield, so therefore the workspace of the robot that we require, or the movement area of the robot that we require, is more like a cube rather than a spherical area that a 6 degree of freedom arm covers. Therefore, in this regard, an XYZ Cartesian gantry is much more suitable. Furthermore, if we talk about the stability of the system, then as we can recall, or as we can talk about, an industrial 6 degree of freedom robotic arm cannot have a human inside its workspace. That is, it is not safe for the human to interact with the arm, as it can be unstable at times. Therefore, an XYZ Cartesian gantry presents a much more better suitable solution, because the workspace of an XYZ Cartesian gantry is constrained, and therefore it's safe for the operation. Integrated design concept consists of a number of ideas combined together. We first generated concepts for each component and then we pruned them, and then after selecting the best out of them we came up with these integrated design concepts. These integrated design concepts comprises of compressed air actuators, that we are using actuators that uses compressed air, and then we use a pneumatic valve for the release of the sealant, and then we have got a microcontroller to control the system of our sealant application. Moreover, as we discussed in the last slide as well, there are a number of concepts with which has a robotic arm. That is, we are using the robotic arm to control the position of the valve so that we can trace out the trajectory with the sealant. And then these have the number of options as we have listed down here, that it is a robotic arm with a motorized valve, then there's a robotic arm with pneumatic valve, robotic arm with hydraulic valve, and robotic arm with pressure regulator. Moreover, we have also got the gantry integrated design concepts. We have got robotic gantry with pressure regulator, we have got robotic gantry with hydraulic valve. So basically these all are our integrated design concepts.
After discussing a number of integrated concept designs, we then had to screen our concept designs to see which was the most feasible for us. After discussing a number of integrated designs, we then had to rank them against the product objectives to see which was the most feasible for us. Material efficiency, time efficiency, improved ergonomics, innovation scalability, the low cost of the solution, durability were all considered as product objectives. After ranking and rating each of these, we found that the robotic gantry system with a motorized valve, microcontroller, and a position sensor was the best solution and was the most feasible. After selecting our final design, we had to break down our system into a number of its components, such as the frame, the motor required, the nozzle, and the controller required for the entire structure. We decided for aluminum extrusions as the main frame structure, having max tensile strength of 45,000 psi, yield strength of 40,000 psi, and a frame density of 2,710 kilograms per meter cube. The motor that we decided was a Cloud Ray closed loop stepper motor. It has the advantage of having a high torque output of 12 Newton meters, power consumption of 360 watt, max RPM of 4000, and a motor resolution of 1.8 degrees. As for the nozzle, which is the most important part of this structure system, was the Nordson Autoflow sealant valve, which has a maximum fluid pressure of 5000 psi, actuating air pressure that controls the flow of 60 to 120 psi. It can withstand cycles up to 40 million, and it has a very low maintenance downtime of 2 hours. To control the entire system, we have a Jetson Nano by NVIDIA, having 40 GPIO pins, an ARM Cortex processor, a power consumption of a mere 10 watts, and an expandable memory so that many trajectories could be stored on a single controller. Now we move on to deciding the timeline for the entire project using a Gantt chart. This is the structure of a Gantt chart, where on the left hand side we have listed the possible activities that may be needed in order to build the entire structure. In June, we will be working on designing the gantry structure and building a CAD model. This will be done by team member Zaryan. Simultaneously, team member Shami will be working on deciding the motor, procuring the motor, and testing the motor to ensure that it meets our requirements. In the month of June, we will be working on and will be working with IMC on procuring the parts and getting feedback on the CAD model that we had built. Simultaneously, team member Shami will work on designing the sealant dispensal system and design the CAD model of the nozzle and the related components for the system. In August, if we are able to get the parts within 1.5 months, we will then work on assembling the system and testing the component that we have achieved. This is the entire breakdown of our Gantt chart. The expected tentative ending time for this project is the end of April, after complete testing and of satisfaction and quality to our own standards. We have kept a time of 1 month for designing the control system, and we have allotted most of the time for the testing of the system to ensure that it meets quality standards, it is safe, and most importantly cannot cause any unnecessary harm to people who are using it. This will all be done throughout the testing process. Now we present the budget, the rough cut bill of materials. For each of the subsystems, the structure, the motor, the belt drive system, the sealant valve and the controller, we have listed down the quantity that will be needed per the structure, the material cost per unit, the material cost per structure, the subtotals and the subsystem subtotals. We have estimated that the sealant application system itself will cost $5,400. We now move on to the second system, which is the transport system. We researched a number of existing design alternatives for the transport system, the first being a monorail track system. This monorail track system has the advantage of being space efficient. It has a simplified installation as opposed to a gantry system, which is very large and requires a lot of space. It's suitable for the linear transportation of windshields within a defined path. However, it is faced with some challenges such as it is limited in terms of its movement, flexibility compared to the gantry systems. It may have restrictions on its load capacity as to how much load it can lift, and the maintenance of the track and trolley system is crucial for its smooth operation. Any gap or any duration in which the system is not maintained properly can be detrimental to its performance. The second design alternative is an underhung overhead crane. It is it has an advantage of maximizing floor space as the transportation mainly happens overhead. It is very flexible in terms of the routing and layout structure and can be integrated seamlessly with other design automated systems. It has a challenge that it requires a very sturdy overhead structure that is capable of suspending and supporting the load. Initial installation costs and complexity may be higher than simpler systems, adding to the capex or capital expenditure, and maintenance of the overhead system is again very crucial for safe and reliable operation. The third and final design alternative is a gantry crane system, which is suitable for handling heavy windshields because of its large and great lifting capabilities. It offers a lot of flexibility in terms of its multiple axes, allowing precise positioning during transportation. However, similar to the last structure, it requires sufficient overhead space for its installation, and the setup cost or the capital expenditure can be very high as compared to other systems. Additionally, it may require skilled operators for safe and efficient operation. Having discussed these existing design alternatives, we then started working on our own designs and came up with 5 integrated designs. Again, after ranking them against the product objectives such as safety, efficiency, ergonomics, innovative and scalability, low-cost solution durability, we found that the system having a motor underhung track, and an underhung track had the highest score. Therefore, we decided to go with this system. We then ranked the designs that we had obtained against each other in terms of the weights that we gave to their different product objectives, the rating that we gave to them, and the weighted score that we had achieved. Then we found out that the solution that was most viable to be developed was the motor underhung track system. Now we shall break down our design into its components. The first requirement is a conical rotor motor, which is a three-phase AC synchronous motor with a rated power of 75 watts, having a weight of 10 kilograms, a 2.5 Newton meter torque output, and a speed ranging from 2800 rpm to 4200 rpm. The second component needed, the vertical beam, which is to provide structural support to the entire structure, is made of steel. The dimension is 10 by 10, the weight is 10 kilograms, and it can. The third component, the hoist motor, which is for lifting the windshield, is a 1150 watt powered induction motor with a lifting capacity of 150 kilograms and a speed of 1200 rpm. And the final, most crucial component, the PLC controller, is for ensuring precision control and safety features.
Through our literature review and by analyzing the existing solution and due to the need of the problem, we developed a rough cut bill of material for our proposed solution of windshield installation in an unconstrained environment of the assembly and production line. The rough cut bill of material has been finalized for each subsystem and contains every essential details about the raw materials, component, and system being used. The table here highlights the amount we need to for each subsystem of our proposed windshield installation systems using overhead railings. The lifting system on, as is mentioned, the subsystem costs around $793. Another subsystem that is responsible for major transport of the windshield is cost around $9,473, and the controller system of the entire windshield installation system is around $666, and the total cost amounts to $10,932. Here on the Excel sheet, you can see the expanded bill of materials, like for the subsystems, lifting system, the windshield installation system. All the raw materials that we estimated in rough cut bill of material are mentioned here. Same as for the transport system over here, and same for the control system. All the subsystem costs are mentioned here, like the 792 and 81 for the lifting system. All quantities required for each raw materials are mentioned in material per cost, and the total cost per material is mentioned. The total system is already also mentioned over here. However, BOMs give a rough idea of the estimate of the funds required for the entire system, which are tentatively finalized. Slight modifications can be needed as the project progresses or if the cost of the material varies until the procurement period.
So this is the Gantt chart for a project. It streamlines the project from May 2024 to the April 2025, which is when the semester ends and the final year will be completed. So in the first 2 weeks of May, we have already prepared the bill of materials, and we have a good knowledge of what materials are required for the project, and we think that we are now ready for the CAD models for the project. The CAD models that will be required will be in our transportation system will be for the gantry structure, CAD model for the gantry structure, and then CAD model for the windshield holding plate. Other than that, there will be motors which will be also structured on the gantry structure, because they will be fitted over there in the actual project as well. After So these two CAD models will be divided in the two members of the project. The green shows member 1 and the pink shows member 2, and the blue shows that both the members are working on that particular activity of the project over the course of those weeks, right? So during the third and fourth week of May, member 1 will be working on CAD models for gantry structure, and the other member will be working on the windshield holding plate CAD model. And in the first week of June, there will be a week for integration of the assembly of the CAD models, basically, and assembling all the CAD models into a complete system, right? And over these 3 weeks, along with these 3 weeks, an additional 1 week, the second week of June, I have kept this time for onboarding partners and gathering funds, since it's really a huge project. We need sufficient funds in order to start work and deliver it to some completion. So these are 4 weeks for our gathering funds and onboarding partners for the project, being on the same page essentially in order to start work for the project. And then from the second week of June, we need to start the procurement. If we have sufficient funds by this time, we can start the procurement. This procurement of the project will be done in two phases. One phase will have the procurement for gantry structure and the lifting subsystem, and in the next procurement phase, we will be procuring materials for the transport subsystem and the control subsystem. Uh, in the first phase, which is from June 2nd to second week of June to first week of July, we will be the member 1 will be procuring materials for the gantry structure system, and member 2 will be procuring for lifting subsystem. And this also includes the lead time. If things work well, then we will be finally having our materials for these two systems at least by the first week of July, and we can then start work later on. But during these 4 weeks, during the procurement time, what the members will be doing is they will be visiting the IMC plant to identify some space where the gantry structure will be made, or the overhang gantry structure will be made, basically. Then identifying the gantry structure, and if the procurement lead time is generally 2 weeks or 4 weeks. So if we receive our materials a bit earlier, we can start building the gantry structure earlier, and by the end of July, we can basically complete the construction of the gantry structure, or if not, it can go ahead by a week or two. And then testing the reliability of the structure is if it is able to lift that much weight or not. This will be done in the this is given additional 2 weeks, the last 2 weeks of July, the week 3 and week 4 of July. Now from the August onwards, the actual work on the project is starting, which is basically building the subsystem, starting to build the subsystem. The first subsystem, which is the lifting mechanism, will be manufactured by our member 1, and simultaneously the member 2 will be working on the rotation mechanism. And these both the members each are given 8 weeks of time, which is 2 months, the August and September of 2024. Then an additional month, each member is given to test their particular systems. During the October, the lifting subsystem and the rotation mechanism both will be tested during the October, 4 weeks of October, right? So these 3 months entirely will cover up the lifting and the rotation mechanism, and simultaneously in August we will be procuring for the next 2 systems as well, which is the transporting system and the controller system. We will start procurement for these two subsystems during the 4 weeks of August, and by the 4 weeks of October, and by the end of October we will have materials. These markings show that the documentation work is also going on along with building the subsystems. So as the members are working on their subsystems separately, they are simultaneously working on the documentation as well. And then by the October, then they again start on the next 2 subsystems, which are basically the transport and the controller system. Member 1 starts on the transportation system, member 2 works on the controller system. Each are given again 3 months of total time, which is 12 weeks, 8 for construction of the system, and then the 4 weeks for testing the subsystems. Right, again the documentation works goes on simultaneously, and in the end we have these this will be the end of January here, and in the Feb and 2 weeks of in the Feb and March, 8 weeks will be given to the integration of the entire project, and entire project and then in the last 4 weeks, which is last 2 weeks of March and the first 2 weeks of April, we will be testing the entire system together here, and both the members will be working on these activities actually. And the last 3 weeks of April, week second onwards till week 4, we will be documenting the entire project, and that is when the project will hopefully end if things work well. That is it. Thank you.
Hello and Assalamu alaikum. Misma and I will be presenting on a constrained assembly line system addressing the situation where the assembly line remains constrained without the possibility of alterations.
So we searched in the market for potential choice solutions, and the ones we found were as follows. The first one is a manual car which is capable of handling heavy loads of around 2 to 15 tons. They can withstand a lot of force, and are manual, so they don't require external power. However, the main drawback is that the dimensions are very big, and also they are very low lying, so it makes it hard for the worker to lift the windshield up. Next we have another card, but this time the card is electrically powered. This removes the motor of transportation. The card will be moving by itself. Again, because it is so low lying, it will make it difficult for the workers to actually lift the windshield up, and also it consumes a lot of power, around 1.5 kilowatts, which is heavy on the system. And then we have the third one, which was a conveyor belt, basically, on which the windshield could move. It can handle a decent amount of weight, and the dimensions are adjustable during the order. So it was better than the other designs. However, the main issue is the fact that if we base a windshield on this conveyor belt, there's a chance that the windshield might be damaged due to falling or slipping off. And also because it's such a big structure, it might obstruct the assembly line. So the design we came up with is a kind of a combination of the two. Basically, what we're trying to do is we are making an inclined plane upon which a So before coming up with a final design, we also looked at the designs and then compared them with each other to see which one was the best. This was our reference design, which is the one which got selected. The other designs would be a switch, which was used to open a system, sirens, which will be used to indicate emergency, and mechanical checks to actually move the system. But we decided I would not reduce stress as much on the team members as our reference design would. Also, the automation would be lacking, and it would take more time. Similarly, for we also had an idea for maglev tracks or electromagnetic tracks, but they were causing a lot of safety issues as well, regards of the current which would be flowing through the tracks, and the cost would be much greater as compared to the reference design. We also had an idea for connectivity, which was better for cost and nearly as much, it gave it nearly as much automation. So after working extensively in a system engineering report, we have come up with the following components for our system. And the inclined plane system would be consisting of angle adjustment mechanism, brakes, steel for constructing the inclined plane, rubber, DC motor, and pulley and pulley belt system. The platform consists of suction cups and windshield holder alongside steel to build the platform, and the safety protocol will consist of buttons and wires.
Components which we are aiming to employ in our system. For inclined plane system, we have angle adjustment, brakes, insulation, motor and pulley. Angle adjustment will help in customizing incline adjustment for enhanced comfort during operations. Brakes within the system will help in maintaining platform stability and prevent any undesired movement beyond operational requirements through the integration of it. Insulation will help further in prioritizing the safety of assembly line team members by incorporating it. Also, further by incorporating effective insulation measures, it will help further in mitigating the risk of electrical hazards within the workspace, whereas motor and pulley help enhancing operational efficiency by employing it, enabling smooth and efficient movement of the platform along the incline, thereby optimizing assembly line productivity. Moving towards the next, for safety protocol system, we have buttons and wires. Emergency shutdown buttons, it will help in enabling swift and decision actions in critical situations by providing accessible emergency shutdowns, ensuring immediate halt of the system. Wiring for control panel connectivity, it will facilitate and coordinate and control by implemented in. It will help the connecting panel and control panel to the operational component, ensuring efficient workflow. For next and last platform system, we have suction cups and stainless steel. Suction cups ensure precise windshield placement and stability on the platform. With the aid of suction cups, we can have a secure windshield holder mechanism. Choosing stainless steel for the platform, it will guarantee unmatched durability and resilience to withstand the rigorous demands of the automotive assembly.
So after giving a rundown of all the components and what role they play in the system, this is our final rough cut bill of materials for now. So the angle adjustment mechanisms, they're going to be four are going to be in use and one costs 55, so that's total of $20. One brake will be used to make sure that the platform is in place, and that costs around $50. The steel which is required, we're going to be using 5 sheets, which are 4 by 8 feet each, and one of them costs $1.76. So that's a total of 8.8. The rubber being used is 2 sheets, which are each 1 square meter, and that will be enough to cover the around 60 inches of the inclined plane. Then the brushes DC motor, we're going to be using 2 DC motors for each side, and they're going to be synced with each other. The pulleys, because they're going to be these motors are going to be 4 pulleys based on either ends and both sides. And those cost $15. The pulley belt, we're going to be using 4 meters of pulley belt, although the system is a little under 2 meters. We're going to be using tri-sealant. So That would be 5.5 and then total of $22. The platform system, so the suction cups, which will be used are already present at Toyota, so that won't cost us any money. And the windshield holder as a whole is also available in Toyota, so that also won't be costing us much money. So the only cost we would have for the platform is the steel to construct the platform itself, which will cost again $1.76 for 5 sheets. The buttons, we're going to be using two buttons, one for stopping, one for starting. So that is around $1.43.
This is our tentative project deadline that we have set up. The green boxes indicates the tasks we have already completed, while the orange ones represent what we plan to do by April 2025.
As you can see, most of our hardware construction will be done before the winter break, and we would also be focusing on getting feedback on the construction so that we can spend most of our spring break working on incorporating the feedback and the last weeks of the spring break in extensive documentation to allow other Toyota factories to also incorporate the system in their assembly line.
This is all from our side. Thank you for your time. If you have any questions regarding this, please feel free to ask.